Good morning, everyone. Good afternoon for anyone across the globe. Welcome to the webinar on the UN Treaty on Plastics, organized by GoPHA and partners. Really exciting to have three panelists and speakers here today on a very important topic in relation to the UN Global Plastics Treaty. And today we're talking about redesigning for circularity, circular by design or designing for circularity. Mixed terminologies about the same subject, basically looking at product system approaches to new material usage. In the end, all plastics are ending up in products, and those products end up in systems. And there's definitely a big issue with how circular these systems are. And that's also why the UN Global Plastics Treaty is happening to call for action and to harmonize legislation around the world to tackle the issue of plastic pollution. So today we're talking about upstream solutions for critical plastic applications. And this is part one out of a two series of webinars. So next week there will be another webinar, which you can also follow through the GoPHA channels, like on LinkedIn and on our website. And you can also register there for free for the second part of this important topic. So for today, few housekeeping rules before we get started. We have three speakers today. Every speaker has around 15 minutes of presenting time, and we reserve the Q&A session after all the presentations have passed. You can leave your questions in the chat room. There's a Q&A button for it. And then our team will collate and select the questions so we can run through them efficiently. Additionally, if you have a specific question for a specific speaker, then feel free to mention the name or the organization name. That's also fine to specifically the person who would you like to answer the question. So the speakers for today are Daniele Spinelli from the Sea Life project. He is creating with his consortium sustainable solutions for plastic substitution, mainly for products that end up easily in the land or in the sea. Jappe de Best, looking at PHAs from residual streams, mainly for also aquatic and fishing applications. And then Helena Vilassa from waste to biocom on biodegradability of the materials used in footwear and other high abrasive product applications. Very quick word about GoPHA, because we are organizing this webinar, and why are we actually doing that? Well, at GoPHA, we strive for driving plastic alternatives in the material space to replace plastics with microplastic-free materials that are derived from renewable feedstocks and that are inherently sustainable, planet-proof, but also human-proof. And we do that with around 60 to 70 stakeholders, including research institutes, including brands, converters, and also material producers. And we're really happy that we can organize these kind of webinars to engage with policymakers and with other stakeholders in the field to make sure that everybody understands what is the relevance of alternatives and substitutes to plastics in our transition to circularity. So a little word about the UN Treaty. As you may know, in 2 weeks' time, there will be the 5th and final International Negotiation Committee meeting in Busan, South Korea. Until now, this dossier has been looking at alternatives and substitutes in different ways. Mainly because, of course, the UN Treaty is talking about plastics. So automatically, the main policy actions are related with plastics, the traditional plastics. Of course, we believe, because PHA, but also other biomaterials are part of this group, alternatives and substitutes to plastics, automatically this is not the key focus in this treaty because we're targeting plastics pollution, right? But still, we believe that it's really important for policymakers to include alternatives and substitutes to plastics as a potential solution to targeting the plastic pollution that we see. And we also see in the past months that actually this topic is either undervalued or understood. Yeah, so there's a lot of need for education, for showcasing, but also making that translation from the different materials that are out there, the different alternatives and substitutes, and translating that to the actual impact that they can make in order to prevent plastics pollution. So really happy that we can talk more in detail about this today. And especially because at the discussions that are going to happen again in 2 weeks from now, we really see a few big challenges, right? Lack of harmonization of information and really a common understanding of where these alternatives can be suitable. Under research chemicals and additives in plastics. So if you work also with alternatives and substitutes, but also with other plastics, it's really important to look at the total system, not just as one material, which normally does not constitute the entire plastic that's being produced, but also globally accepted assessment criteria and standards, and also looking at, what actually entails this group of alternatives and substitutes, and what is the boundary of that scope, and where do we become conventional plastics. So that's also really important to have further clarification on that. And then at the moment, there are limited mechanisms for technology transfers, for trade infrastructure and financing. Also, these transitions which require a lot of capital, a lot of knowledge, and that all has to be harmonized and being executed. Of course, if you go to the top right corner of this slide, there's a big significance of having a global instrument. We see, of course, a lot of, let's say, bottom-up regulations and policies, such as Single-Use Plastics Directive, packaging and packaging waste regulations, microplastics regulations. But really here, it's an opportunity to have global harmonization for an issue which is inherently global. Our oceans are from everywhere, and they're communicating with each other in terms of the pollution flows. And more importantly, the plastics business is a global business. We're using the fossil feedstocks. We ship them all across the world. We convert them into plastics that are getting shipped all across the world again, and then we're using them globally. And then the pollution ends up in the global seas. So it's really important to have that harmonization around that topic. And then, of course, what we see as potential impacts to have these unified global policies also would mean that together with the group for alternatives and substitutes, we can really harmonize towards action. We can select certain application areas, we can select certain standards and really implement that on a global scale. So this is a really big opportunity for all of us. And then, of course, together, we should be able to grow these sustainable markets as well. Very quick recap on the involvement of the work that we've been doing in the UN Treaty. Basically, this whole process started in December 2022 already. So in 2 months, it's about 2 years of this process. There have been and there will be 5 international negotiation committee meetings, of which the last one you see at the very end of this timeline happening in 2 weeks in November in Busan, South Korea. In between, we have, of course, been attending some of these meetings in Paris, in Ottawa, and different locations. And always in between these meetings, there's always time to influence policymakers. For example, on the left side of this slide, you see the UN expert group's recommendations. Across the world with our community, we have recommended experts in the field of microplastics pollution, pollution in general, biodegradability, compostability, but also material science, and have recommended these experts to, let's say, the individual negotiation teams of the individual countries. In between, we have organized webinars like this, put position papers in place, and also engage directly with some of these negotiation committees. So Just a last note here on what we're going to do today. We're going to look at the critical application areas where we really see a big impact and a big potential for alternatives and substitutes, especially because there are a lot of application groups where automatically, let's say by design, these applications end up in nature, either in the soil, either in the aquatic environment, or even sometimes in our human bodies, for example, with medical applications. So today we're definitely going to explore what's out there, what sort of projects, what sort of consortia are working on these themes, what is the impact that we can have if we would transition to using sustainable alternatives to plastics in these areas, and what should also be done at this UN treaty negotiation to actually make room for these kind of applications and also the use of these materials. So with that, I would like to stop my introduction and invite the first speaker of today, Daniele Spinelli from the Sealift project, and he's going to talk 15 minutes about his consortium and his project. Daniele, please share your presentation and go ahead.
Okay, thank you for this opportunity. And so I think that you can see my screen. Can you see?
Yes, it's coming.
Okay. Okay, so good morning. My name is Daniele Spinelli. I'm a project manager at Next Technology Technotextile. We are a textile research institute with the main focus on innovative solution for industries. So today I will give you an overview of Sea-Life project. It is a project funded by Horizon 2020 program and was just finished 2 years ago. And I will explain you how the use of bio-based material has produced quite good results for different market application. Just a short introduction. Our organization, as said, was founded in 1972 with a support to support textile companies, mainly to use more sustainable materials in terms of innovative solution for products and processes. We are an organization of 27 people with a main focus, as said, on textile, but we are also quite involved in technological innovation and transfer, mainly, and also testing for textile sector through our certified lab. So we are mainly, our main business is focusing also on circular economy and circular bioeconomy in order to promote bio-based materials for a sustainable textile industry, not only referring to fashion industry, but also to technical textile application. So as I said, our organization is also part of bio-based industry consortium. So we are promoting the use of bio-based solution in terms of a new biopolymer for textile application, but also for new biochemicals for textile finishing process. Our organization is also supporting companies through different consultant services, starting from raw material selection to final products, material surface functionalization, development of novel chemical processes, and also try to identify a circular approach for sustainable textile practices. We are also connected to other different industries, mainly involving in other sectors like packaging, automotive, furniture, and building. And we are also promoting new devices for textile companies, as said. We are also supporting companies for environmental monitoring of their environmental footprint by life cycle assessment methodology. going a little bit on detail, why use of biopolymer is interesting for textile. The use of biopolymers in textile, I can say that is starting not so much a long time ago, but now is becoming very, very interesting to find alternative to fossil-based polymers that are currently used for textile industry. Or sure, I'm referring to conventional polyester or polyamide that are, for sure, speaking about polyester is covering a huge amount of the textile market at the moment, around 54%. So biopolymer are also diffusing in order to obtain a new type of fibers, yarn, and to make new textiles. Sure, there are different biopolymers that could be extracted from natural sources, or PHA or PLA, or polysaccharides or proteins that could, for example, be used for textile application. But in any case, bio-based fiber production is constantly growing as a possible solution for the market in order to reduce, in any case, the environmental impact of the textile industry. So biomaterials in general could be used for different textile applications. So sure, biopolymer could be used in manufacturing on new fibers and then obtain woven and non-woven structure for, as I said, for garment making, but also for insulation materials, for example. But could be also quite used for technical textile application, mainly referring to wound dressing or drug delivery or filtration media. But recently we are also having good opportunity to substitute fossil-based compounds for the textile finishing. So this part is really attracting the market at the moment. I'm referring to processes that are connected to dyeing, but also finishing in terms of functional properties that need to be included at the surface level on the fabrics. For example, I'm referring to anti-static properties or antibacterial, hydro and oleophobicity, flame retardants. So there are a lot of options in terms of biomaterials at the moment on this field. And sure, bio-based polymer could be also used not only to make fibers, but also for finishing of textiles as alternative to fossil-based compounds. So sure, there are different options, and the market is also attracted from these new opportunities. What is the current market of bio-based polymer for textile? Sure, we are following the polymer availability. We can say that, for example, bio-based PET at the moment is covering the large percentage of the polymer used for textile application. But in any case, there is also a technical textile research that is moving also towards the use of bio-based fibers in general. Sure, probably another one that is quite known on textile application is PLA, but also PHA is starting to be more attractive for different textile application, because in general we need to overcome some limits in terms of mechanical properties that are currently affecting the market penetration of biopolymers like PLA. So there are a lot of research ongoing on this field, and I'm sure we are going in the direction to have a blend of polymer in order to have a fine-tuning of mechanical performances that are quite close to conventional polyester or polyamides, and in any case fossil-based polymer for textile. Bio-based fiber also could be used as saved for different technical textile production. For example, could be several examples are available, like PHA gauze weave used as a mesh for tendon repair, or use also or natural fibers for geotextile application as for soil protection and reinforcement. And this material could be also coated with other bio-based polymer in order to keep properties for a long time, so also in terms of durability. We have also example on using of nanofibers that could be quite applicable for realization of non-woven mesh, mainly for biomedical applications. So in this sense, there are some developments for scaffolds for tissues regeneration or for drug delivery system or diagnostic in any case. So also for this part or for this research, we can use a different biopolymer through the electrospinning technologies to obtain a nanofiber network. Biopolymer could be also used to produce mono and multifilament that are obtained by melt spinning process. And so through this process, we can test a different type of bio-based fibers like PLA or PHA, or a blending of this biopolymer with other additives or other biopolymer in order to improve key mechanical performances. But in any case, several projects have shown that PLA and PHA can be melt spun with successfully, also quite close and comparable to petrol-based fibers. So here you see some example. For sure, the spinability is also connected to key properties of materials like viscosity and also melt flow index and other key parameters that needed to be optimized during the process to obtain a fiber quite close to the specific market needs. So going in detail about C-Live project. C-Live was a project said funded by European Union under Horizon 2020 work program. It was an innovation action with a main top funded in the topic related to sustainable solution for bio-based plastics on land and sea. So as said, the project ends last year and was coordinated by TENE, that is a technological institute from Valencia. And the consortium were composed by 24 partners that mainly were across Europe and also involving a connection with South America. So the total budget of the topic was 10 million euro. C-Live project were inserted in a strategy that is related to reduce the plastic pollution, mainly avoiding that million tons of plastic usually ends in our ocean and contaminates our land every year. So according to this, the project purpose was to give a positive reply for this in order to use and promote bio-based plastics and also try to overcome current limitation for these materials. First of all, also thinking that the recyclability with the current technologies. So the strategy of C-Live was mainly to boost the use of new bio-based materials and contributing to a circular economy with a cohesive bioplastic strategy. And also, so one of the goals of the consortium is to support the European plastic strategy, mainly focusing on different aspects and also involving specific experts for the development of bio-based plastic solution using sustainable biomass sources. You can see also here algae. Optimize sustainable business model and the product design strategies for new solution. Support pre-normative studies to foster standardization of biodegradable solution, and promote the use of new solution also through industries, public authorities, and citizens in general. So mainly to give a development for European and global plastic frameworks for policymakers. For sure, as said, we have taken into account end-of-life solution in order to have a circular bio-based economy. So C-Live has generated a different solution. We will focus on improvement of properties, but also to improve the efficiency of the current technologies, and also the design connected to end of life. The solution has been upscaled and demonstrated by 8 end applications in 6 regions, mainly across Europe and South America. We were focusing on packaging materials, thinking mainly to rigid materials, but also flexible frozen food packaging, single-use plastic cutlery, and mulching film, and harvesting bags in order to have biodegradable in soil materials. For sure, we have also focusing on sea application, thinking to fishing nets or fishing crates, oyster mesh bags, and fish crates. Yeah, just an overview with the main focus sure on fishing nets and oyster mesh bags, which our organization has contributed for the material development in terms of bio-based formulation, spinability, and material testing in comparison with conventional materials. So, for example, we have used as a benchmarked material monofilament in HDPE, and conventional oyster mesh bags that are made with HDPE and carbon black. And in both cases, we have tried to investigate also the use and the aging of materials in order to understand what are the performances during the time and during the end of life, and also test what is the end of life in case of damages and losses in the ocean and sea. So in terms of main conclusion, we have observed that usually bio-based formulation needed to be improved to meet the market needs, mainly if we are referring to tenacity of materials. This sure is these are the current limit of some bio-based polymer, and we need to overcome this through blending with other bio-based polymer and also blending with other additives that in any case could improve the mechanical performances of the materials, for sure. In this case, referring to mono and multifilament. So key properties for sure are the tenacity, but also UV resistance, because fishing nets and oyster mesh bags are in contact with a saline environment, and also under different UV condition, because it's not the same to test the materials in the Northern Sea or in the Mediterranean area. So also this part needs to be taken into account. And sure, the degradation under marine environment. What we have said, so possible alternative could be founded, and also alternative to conventional fossil-based materials. And in any case, we can reach also quite good compromise in terms of biodegradability and recyclability of a material. In any case, also the environmental impact, and also the biodegradation need to be evaluated by specific standardized methodologies. But for sure, that was one of the aim of the project. And that's all from my side.
Thank you, Daniele, for the contribution, and we'll talk to you further in the Q&A. So now I would like to invite Mr. Jappe de Best from MNext to present next. Jappe, please go ahead.
Thank you very much, Rick. I will share my screen. So I hope you can see it now. Okay, I see a yes from Rick, so thanks. So good morning, everyone. So my name is Jappe de Best, and today I will tell you something about the production of PHA from residual streams, about opportunities and challenges in this matter. But before I will start, I would like to thank the organization of GoPHA for giving me this opportunity to tell something about our work on PHA. And today the presentation that I give gives an overview of different research projects that we have been conducting in the past 8 years, which are funded by Interreg and SIA. So quickly about myself, who am I? As I said, my name is Jappe de Best. I'm a professor in bio-based resources and energy, with a background in microbiology as a main topic. And I work at Avans University of Applied Sciences, and more specific at the Center of Expertise MNext, which is founded in Breda in the Netherlands. And if you look at MNext, it's a center of expertise which focuses on material and energy transition. That's also what the abbreviation is about. And it's a center of expertise which is a cooperation between two universities of applied sciences. It's Avans University of Applied Science and the University HZ of Applied Science, which is founded in the province of Zeeland. As I already told you, we focus on the acceleration of materials and energy transition, and we do that by conducting applied research, which in this case means that we do all our research together with mainly SMEs, but also with education and society. So about our activities, we have 3 pillars. So we have educational innovation, we have business support, and we have applied research. And obviously today I will mainly talk about applied research with a link towards business support. And when you look at the different research groups that we have at MNext, here you see an overview which ranges from energy on the left side with renewable energy carriers, to all the way to the right side, we have a research group on marine bio-based chemistry. And when you look at my research group, it's somewhere in the middle, so bio-based resources and energy. So we focus both on materials and energy, but always with bio as a starting point. So about our research group, so our main focus is the recovery of valuable bio-based building blocks and energy from residual streams. So that's also the topic of my presentation on PHA. So we always start from a residual stream, or what's now mostly called a waste stream, but I prefer residual stream because I consider nothing as waste. Everything could be used as a valuable building block. So when you look at those residual streams, we focus on residual streams from industry, agriculture, and nature. And when we look at processing, we do this through biological, chemical, and mechanical processes. And today the PHA will be mainly focused on biological production of PHA. Well, why do we do this? When we look at our motto, this is always the one that I use. So we all know it's not easy being green. So what we aim for with our research group, together with our partners, is to help companies, governments, and also the general public to make steps in becoming more green. And that also brings me to today's topic, so about PHA. So this is a bit the overview that I will talk to you about. For who doesn't know yet what PHA is, I'll briefly introduce it. Then why do we focus on PHA, and what is our approach in this? How do we make PHA, and how do we relate this to a product market fit? And finally, I'll briefly touch upon some challenges, and I also will give some recommendations towards the UN treaty. Well, as a first start, what is PHA? So PHA is the abbreviation of polyhydroxyalkanoates, which is a polyester. And what's important to know is that PHA, in this case, is produced by bacteria, and they use it as an energy or carbon storage. I have a good colleague who always explains when we eat too much fast food, then we store it as fat, and these the bacteria don't store it as fat, but they have the nice way of producing PHA. And in fact, PHA is not one polymer, but it's a family of polymers. So it's HB, HV, and HH. So it's a mixture, and beneath you see the chemical structure of PHBV. So why do we focus on PHA? Well, it has many advantages. So it is a bio-based polymer. It's biodegradable, both in soil and water. You can see an example of in soil on the left bottom side. It's biocompatible and recyclable. It's UV stable and also has a low permeability, which gives lots of opportunities for applications. And we think it can play an immediate role in the material transition that we focus on. So when we go to our approach, our starting point is always the circular value chain. So we start from a resource, and then we always look in the complete value chain. So the pre-processing, also storage when it's applicable, final processing, again, storage if you have the final product. Then you always have the user phase, and obviously you have disposal at the end. And we always hope to make it circular so we can use it as a resource again. And in this case for PHA, we focus on residual streams. And the first step for us is always what's the availability of these residual streams, which processing is needed, and also what type of carbon source are we dealing with. And on the left side, I gave some examples of residual streams that we use. So on the top left is whey as a residual stream from cheese production. The brownish one is the residual from beer production. Bottom left is the residual stream from potato processing. Well, this shows the potatoes, but at the end you also have a residual stream. You could also use juices, which is on the top right side, from different agricultural materials. So for instance, the leftovers from tomato or pepper production. And on the bottom right, you see sewage sludge from a sewage treatment plant, which also can be used as a starting point for PHA. And I found it nice that this really aligns with the vision statement of GoPHA on the Global Plastics Treaty, where they mention that the use of renewable carbon feedstocks and not fossil carbon. And I think this is also our starting point. So how do we make PHA? Well, this is when you look at circular, I made it a linear line for now. So we have an organic residual stream on the left. Then we have pre-treatment of this residual stream, bacterial PHA production, extraction, and then we process it further until end of life. And when you look at it in a more complicated schematic, then on the left side, you see the feedstock that we use, so the residual streams. Then we first have an acidification step of the residual stream where we produce volatile fatty acids, so like acetic acid, propionic acid, lactic acid, although that's less suitable. Then we have an enrichment step to enrich the biomass that produces the PHA using those VFAs. And in the end, we have the accumulation where you have the PHA-rich biomass. And we use for this mixed microbial culture. So you often see that PHA is produced by pure cultures, but we use mixed microbial cultures in a non-sterile environment, which gives some opportunities, but also some challenges. Well, then next we have the downstream processing, where we have the drying, extraction, and in the end extrusion. But we also look into the direct application of PHA-rich biomass, so without the first extraction, which has the advantage that it can give a cheaper product. And in the end, we have different ways of application of PHA. So we look at injection molding, filament printing, film blowing, and also 3D printing as a final product. Well, here gives an overview of these processes that we mainly do in our laboratory. So on the top left, you see the biomass in the beginning, before we start producing PHA. And on the right side, you see it after we have produced PHA. So you see it completely turns white as the color of PHA, and bacteria are 80 to 90% full with PHA. Then we have the extraction that we do, and this is one of our end products on lab scale. And here you see some on the top, on the bottom right, when we make some products of this. And when I go to products, because it's always important when we look at products that we want to make together with companies on from PHA, that we use at a product market fit. And this means that we look at products that have an added value if you use PHA, either because there are strict environmental regulations. For instance, hopefully when the UN Treaty is signed, there is a strong consumer emphasis. So it means that consumers are really into sustainability and they would like to have a more sustainable product for use. And the final one is when you have biodegradability as an added value. And to give you some examples of it, so what we looked in one of our projects, we worked together with a Finnish partner, and we asked this partner, so what would be products that you can use that now often end up in nature where biodegradability could be a big advantage? Well, I will show you 3 of them. So first one is a mud guard with a bike. They often lose this when they bike in nature, and what they now end up as a lot of garbage. And it could be very useful if this could be, if it ends up in soil, if it could be degraded within a limited amount of time. So this is also a PHA which we use, the orange one, which is a mixture, by the way, of PHA from residual streams and a commercial PHA, because we were still on a pilot scale. Second example was the production of golf tees, which also often are lost and end up in nature. So their biodegradability also has an advantage. And the last one, which was also a starting point from this presentation, if you have the link with the UN treaty, was producing a fishing lure. So on the top right, you see the 3D printing of this fishing lure. And on the right, you see an example of this one. And I hope the movie works, so we can also show we tested it in Finland in this case. So here you can see the use of the fishing lure. And why this fishing lure? Yeah, obviously, often when a line breaks, they end up in nature, and now often metals or even lead are still being used for this, or plastic based on oil. So if we would have been using this one and ended up in nature, it would have been degraded in a limited amount of time. And when you look, I think this also nicely aligns again with the vision statement of GoPHA to use marine biodegradable materials to eliminate microplastic pollution. But I also would like to add that although not in this UN treaty, it would be very important to extend this also to freshwater and also to agricultural applications, because those agricultural applications are also one of those products we look into, for instance, agricultural foil or plant pots, where also biodegradability has a big advantage in usage. Our remaining challenges, we are on the scale with our partners towards a full-scale application of PHA on residual streams. But what's important that we are still focusing on a more stable and constant production process, especially when you use several types of residual streams to produce your PHA. Hand in hand, it goes with process optimization to achieve more competitiveness on price and quality. Especially, well, everyone knows it's hard to compete when you have a new product which has to compete with conventional plastics which have been developed a long time ago and are already completely optimized. The third focus is the acceptance of products from waste streams, which sometimes also is something to worry about. the public acceptance. So we need to explain why we do this, what we do, and that in the end it gives a safe consumer product. And there's always the link with legal compliance. So how do we deal with this one? I was asked to also make a link with the UN Treaty or to give a message to them. So our recommendations on behalf of MNext. I already mentioned, do not limit the UN Treaty to marine environment, but also include freshwater, and even more extended to agricultural products as well would be very nice. It was already mentioned by Rick, but also give a clear mandate to the use of renewable and biodegradable materials such as PHA. And I think in this matter, it's also very important to address, when addressing alternative plastics, we should make a better distinction between bio-based biodegradable plastics and bio-based non-biodegradable plastics, because there's a lot of confusion about these topics, not only with the general public, but also with people from governmental organizations and also with industries often. I would like to finalize by saying that definitely I don't do this work all by myself. So I have a big team which actually does most of the work in the lab. So here you see a picture of my team. And as I mentioned several times before, we work together with a lot of partners in different types of products. So here you see, projects. So here you see an overview of some of our partners. And with this, I would like to end my presentation.
Yeah, thanks, Jappe. Very nice overview. I think we keep the Q&A for after the presentation.
Yeah, that's what I understood.
Yeah, thank you. So next speaker is Helena Vilasa from Waste to Biocomp. Helena, could you share your presentation and go ahead?
Yeah, sure, thank you. So I'm going to share. Do you see my screen? Yeah, so perfect. So as Rick said, I'm Helena. I'm going to present some results from the Waste to Biocomp project, namely biodegradable materials for footwear and textiles. Sorry, this is not passing the slides. Okay, so just a brief overview. I'm going to start to present CITEV, the entity that I work for, and then have an overview of the projects and focusing on the footwear and textile industries. And then present the use cases that we are developing in the project, some results and some challenges that we are facing, and present the overall concept of the circular loop that we have in the project, and then the relation of the project with the UN Treaty. So CITEV is the technological center for the textile and clothing industries of Portugal. CITEV has a wide range of services, namely the testing of quite a wide range of different tests for the textile products, also product and process certification, research, technology development, services related with sustainability and circular economy, and also the digitalization and Industry 4.0. We also have training and coaching activities, support to innovation capacities, and others. CITEV is focused on markets, namely for fashion, sports, defense, and personal protective equipments, mobility and transports, workwear, health and well-being, and also for architecture and construction. Now, going to the project Waste to Biocomp, which comes from converting organic waste into sustainable bio-based components. This is a European project funded under the Horizon Europe program. It started in 2022 and will come to its end in next year, in 2025. So, Waste to Biocomp gathers a consortium of 13 European partners. We have 3 from Germany, 2 from France, 1 from Spain, 1 from Switzerland, 1 from Italy, and 5 from Portugal. And in here we gathered 5 SMEs, 3 large industries, and 5 research entities. The main goal of the project is the relevant scale production of bio-based products and materials as alternatives to traditional fossil-based materials, using innovative manufacturing technologies and following a closed-loop approach. The project covers three value chains: the footwear, the packaging, and the textile. And to all of these, we also apply the inkjet printing. Today, I'm going to focus on the footwear and the textile. Now going to some problems, challenges, needs that these industries are facing. The main one being the pollution that they cause in our environments. For example, the footwear and textile industries together, they are responsible for 5 to 10% of the global pollution impacts. We have numbers as, for example, 17 million tons of textile waste, 1.2 million tons of shoe waste, and these are rising each year. But they still have a lack of sustainable alternatives. What do we consider sustainable alternatives? We consider polymers or materials that are easy to process, that have low costs, or at least equivalent to the current costs that these industries have, but having good properties, and of course, they must come from renewable sources. PHAs, polyhydroxyalkanoates, they appear as promising alternatives, as given their properties. I'm not going to go through them, as Jaap de Best has already presented the properties of these polymers, but we still have limited production. The PHAs available on the market are still quite limited, and their properties are also still limited, which leads to limited possible applications of them. As an example of this, in 2020, the PHAs represented only 1.7% of the market share of bioplastics. This is why Waste to Biocamp has appeared, and it comes with some solutions to cover these problems, namely by developing biodegradable and recyclable biopolymers for shoe foams, both insoles and soles, and textile coatings. These ones having similar physical-chemical properties to conventional plastics, and as they come as replacements for example, polyester, widely used in textiles, and for example, EVA, which is quite used in shoe foams. But also, the project also develops bio-based pigments as replacements for fossil-based pigments, and also develops other bio-based solutions, which I'm not going through them today. In terms of trying to cover these needs from the PHA market in itself, Waste to Biocamp is producing PHAs using scalable processes with a lower costs and higher properties range, a quite wider properties range, and is using the PHAs not only for the base materials, let's say so, but also to produce additives for these materials, like, for example, capsules and particles. Now, going to the use cases of the project, we have 4 main use cases, namely shoe soles and insoles using compounding and foaming processes. We are also developing plastic films and packages, both flexible and rigid ones, using blown extrusion and thermoforming. We are developing bio-based textiles, namely technical textiles for sportswear and shoes, using spray and coating techniques, and also developing different printed substrates using bio-based inks, bio-based pigments, and the inks developed with these pigments through inkjet printing systems, both for 2D and 3D substrates. Today, I'm going to present you the use cases for the footwear and the textile cases. Going for the footwear, we started with different organic waste carbohydrate and recycling routes also from the project. recycling sources, and also different natural oils, proteins, and other bioactive principles. And with this, we have produced different PHAs, as I said, with a wide range of properties, namely quite wide range of crystallinities. They are produced both by biogenesis and by chemical routes. Of course, the chemical routes, it's the chemical modification of the PHAs produced by biogenesis. In this case, for biogenesis, we have been using cyanobacteria. As for the PHAs modified through chemical approaches, we have been able to go to a 5 kilogram scale per batch and using solvent-free methods. Using both the PHAs and also proteins and other bioactive principles, we have also been produce different functional capsules. In this case, we have also achieved a 5 kilogram scale. We produce different capsules that are quite stable and with essential oils encapsulated. And depending on the essential oil that we use, we have been able to achieve capsules with very good antibacterial properties. Combining the PHAs and also the capsules, we have produced bio-based foams. And these ones can be, if coming from the PHAs, we produce PHA-based foams. We have here some picture of the foams with different percentage of PHAs and with different hardness levels. But we have also been able to come in, for example, from biopolyols that are available, we have been able to produce also bio-based polyurethane foams. We are now on the phase of developing the soles and insoles using these foams. We have here an example of a polyurethane-based foam that was grown, let's say so, on a textile substrate, directly on a textile substrate, so we obtain a final insole. And we are also, of course, developing recycling processes, chemical recycling processes for these materials, and we are going to test their biodegradability with the goal of obtaining materials to feed the process again from the start. In terms of the recycling of the biopolyurethane foams, I can say that we have already been able to recycle a full the insole, these soles that we have here in the picture, we have been able to recycle using microwave assisted chemical recycling and reobtain the biopolyols to produce again polyurethane foam. Now going to the bio-based textiles, the textile value chain. Again, here we started with the same, the carbohydrate wastes and different bioadditives to produce the PHAs, same as before. And with these PHAs, we have developed some bio-based fibers using wet spinning. As an alternative process to the melt spinning, we try to obtain fibers through a different process to check their properties. However, in this case, we always needed to use organic solvents for this process, so it's not feasible to upscale this one, so we abandoned this alternative. But with the PHAs, as I said, we're developing coatings and we develop different bio-based coatings. We produce different coatings through spray technology and also knife coating. We are now in the process of improving these coatings, namely the uniformity and characterizing them to see all of the properties. And with these coatings, we are developing technical textiles, as I said, for sportswear and also for shoes. And then we are going to recycle them and also test their biodegradability. Of course, to prove that or to show that what we are doing it's really sustainable, or it has a sustainable character, we are doing life cycle assessments of the different processes. And as you can see, for example, in terms of energy spent in the processes, if you can see on the left, we have the PHAs produced two different scenarios of the production of the PHAs in the project. And on the right, we have different polymers and also the PHAs that are on the market. And we can see that the PHAs produced in the project have a lower energy profile than the ones on the market. So we have quite promising LCA results. Now, just showing the circular loop that we aim here to achieve here in the project. We started with the production of the PHAs, as I said. From this one, we developed the different biomaterials, then the final products that go to market. And through different chemical recycling approaches, we can reobtain, let's say, so the monomers and also other molecules that are present in the products and use these ones to produce again the PHAs. But as I said, we have other materials that are not PHA based. So with different molecules, we can produce biomaterials, for example, the polyurethane foams, and then produce the final products. And through, for example, microwave-assisted chemical recycling, we reobtain biopolyols, which can then be used again to produce the foams. Now, how is Waste2Biocomp contributing to the Global Plastics Treaty? It is developing alternatives to fossil-based plastics with properties that allow a quite wide range of applications. These are recyclable plastics, but they are also biodegradable plastics. They are non-toxic. They are produced through solvent-free production approaches. So it contributes to human health, contributes to environment safety. The monomers and other additives that we obtain through the chemical recycling of the materials can be used for the new production of these plastics. So we have here a closed loop, as I just presented. And we predict that with the further upscale of these processes, of this production of the PHAs, we'll obtain a lower production cost. So we have a higher potential of adoption from the industry. Namely, we already have some companies that are interested in this process. Some recommendations for the negotiators. They should focus not only to promote recyclable polymers or recyclable plastics, but also the biodegradable ones to avoid the microplastics pollution that comes from the release of microplastics from these materials during their life cycle. They also should set some labeling requirements. For example, make mandatory to divulge the percentage of recycled content, the type of recycling, because some consumers may not understand, but a lot, and we are increasing these numbers. A lot of consumers are interested in this, and they can understand that having a product coming from thermal or mechanical recycled polymers is not the same than getting chemically recycled polymer. Also, the source of the materials for these recycled products. The information should be traceable in the producer to avoid greenwashing. And also, of course, we need a clear definition of terms that are being used. And they also should try to avoid unfortunate replacements. Unfortunate both in size of the chemical safety of the replacements and also in terms of the environmental impact of the replacing polymer or the replacement plastic through, for example, LCAs, mandatory LCAs for all the materials, for example. And that's all from my side. Thank you all for your attention.
Thank you very much, Helena, for the nice presentation, and thanks all panelists for your contribution. I would like to invite all the panelists to switch on their cameras for the Q&A, and I would like to invite all the participants to add your questions in the Q&A box. It's on the bottom side of your screen, and you can type freely there. In the meantime, I will just get started with the first few questions that we got. So here's something about barriers for adoption of biodegradable alternative materials. Question to everybody here in the panel. You know, there's a lot of interesting R&D work being done. How do you see scaling up these sort of solutions in terms of policy, financing, or market adoption? Any thoughts on this? Who would like to start?
So if I can start, I think that in terms of market adoption for textile, we see at the moment a limit that is connected to the biopolymer availability and also the cost. For sure, as you know, as all of us know, the market penetration of these materials has at least referring to textile, but probably could be extended to other industrial application. These are two main challenges that we need to overcome if we want to push the market in this direction.
Thank you. Anybody would like to add to that?
Yeah, I would like. I guess I agree with Daniela. Indeed, so first of all, the production capacity at this moment is limiting, and obviously also the price is still, it's 2 to 3 times more expensive. But I also know from a lot of companies that is not always the limiting factor. So I think we should also tell in my presentation, you should find the markets where people are willing to pay a bit more for a bio-based plastic in comparison to a regular plastics. And on the other side, then the price in the end will go down anyway, because when we have more production facilities, then also, and process optimization, then obviously the price will also drop. And at the same time, I also think that, for instance, a UN treaty, but also legislation more on this fact from governments, that needs to go hand in hand, because otherwise I don't think we will make the step if we have to do it all by ourselves. So for me, it would be a combination. And what I also see, and that's also very nice, because I think 2 weeks ago we were on the Dutch Design Week in Eindhoven, presented some of our projects, and then you see that people are really interested, but often they don't know. So it's also very interesting to have more information to people what the alternatives are, and showcase those alternatives. So I think that will also help.
Thank you. How about you, Helena? Would you like to add something?
Yeah, I can say. I must say that, of course, I agree with what has been said. Of course, the availability of the feedstock needed to produce these polymers, and also the biopolymers available on the market. Its availability is quite limited still, and of course, the cost. The cost is a huge problem. As has been said, of course, there are some companies and some consumers that do not mind paying a little bit more to obtain more sustainable solutions, but those are a limited range of consumers and of companies. So it's really important to decrease the cost of production, because 3 to 4 times higher is too much. But as has been said, as we are developing new processes, new production processes, new biopolymers, and increasing the scale of production, the cost is going to lower, of course. And but having some legislation that accompanies this, and some investments in the research side by side, it's quite important.
Yeah, thank you. So another question from Jesper. Thanks for the inspiring presentation. I was wondering if antimicrobial properties don't impair the biodegradability. Can those two properties coexist? I think it's a very interesting question. Who would like to answer that one?
I can say something, because I mentioned the antimicrobial capsules. No, they do not impair the biodegradability, because in this case, the antimicrobial comes from essential oils. So they are inherently also biodegradable. So we won't have that problem.
All right. So the active ingredient that makes it antimicrobial is not impairing the biodegradable process.
Yeah.
Good. Few questions from Nidia. One is for Sea Life, for Daniela. The blends that you presented, PLA, PHA blends, are they actually PLA, PHA blends, or are there also other materials in there? And are they already commercially available, or are they still in development phase?
Yes, we have used a blend with focusing on PHA mainly. I'm sure we have included other additives and also other bio-based polymer to improve material performances. I think that the material is still in the development phase, but it's the mechanical properties that we obtain are quite good for monofilament compared to conventional fossil-based materials.
Okay, very good. Then a question for Jappa from MNext. What type of PHA building block did you produce and do you use in the project?
Always unmute first. So the type of PHA that we produce at the end is always a mixture of HB and HV, and the composition of those always depends on the residual stream, the starting point that we have, because depending on the residual stream, you produce different types of volatile fatty acids, and the composition of volatile fatty acids determines the type of PHA that you produce. And that's also one of the things that we are looking into. And I briefly mentioned mixtures, using mixtures of residual streams, because in the end, what we would like to achieve is that we can predict in advantage which type of PHA we can produce. So either more brittle one or less brittle one. So that's one of the focus points. And to add to Danielle, to the question about additives, that's also, I didn't touch upon it today, but we also look in ways to have different properties of PHA, for instance, by adding different types of fibers that also tweaks a bit the biodegradability of the material. And at the same time, another line of research is, for instance, adding biochar as a component. And that all has to do with what type of properties do you end up with, and also how fast can it biodegrade, because that also depends on the application that you use the PHA for.
Absolutely, yeah. Thank you. And there's a follow-up question actually on this topic, so I'll just fast track the question from Isabel. So how consistent are your PHA yields and also the composition, in terms of the copolymer content? And how does that relate to the variability of the feedstock? So therefore, I would like to ask it now. Can you actually control this VFA composition in order to steer your production process?
Yes, we can, especially when you have one. Obviously, it also depends on how stable the residual stream is. So that's always a bit within a certain bandwidth. If you have a rather stable composition of your residual stream, then after adaptation of the mixed microbial culture to the new residual stream, we have a very stable VFA production. And thus we also know which PHA we will produce. And if we see that there is a change, of course, you can also add a certain amount of VFA, a more pure one, to steer that you still always have the same composition of your input stream for PHA production.
Mm-hmm. Thank you. Then last question from Nidia for Helena. Do you think foamed PHA can be easily scalable and ready for industrialization? How do you process the PHA? Is that under extrusion, foaming, or a different process?
So I'm not sure if I heard for the foam, precisely for the foam,
It's
right?
the foam.
Yeah.
So how easily can that be scaled to industry standard? And second, what process do you use to make these foams?
It's foaming process, and actually it's already being produced in a company, in a large industry. They, of course, they are producing still in a lab scale, but they are using the same process that they use in a wider scale, in an industrial scale. So we foresee that they won't have any problem. We might have a limitation on the amount of PHA that we can have in these foams. Of course, it's not 100% PHA, but we are mixing at the moment. We are mixing the PHAs with some bio-based EVA, which is already available. So we have foams with above 90% bio-based content already. And we do not foresee issues with upscaling because the process is the one that the company is already using in their industrial process.
Okay. And just a follow-up question from me is the introduction of the bio-based EVA, how does that then affect the biodegradability?
We still need to check that. Yeah,
okay.
We have not made the biodegradability of these foams.
And for the foaming process, is that an extrusion foaming process or an injection foaming process or a different process?
I cannot say, sorry.
Thank you. Then question, okay, one follow-up question on the foaming. Could you share the name of that industry company?
Oh, sure, it's Nora from Germany.
Oh, okay, thank you. Another question on recycling. Maybe it's for Jappe or for Helena. Normally or today, introduction of alternative and substitute plastics like biodegradable materials are actually considered as a contamination in recycling processes, and therefore a lot of plastic recyclers don't accept it. How do you think from a systems perspective should we deal with that? Should we have separate garbage bags? Should we have separate labeling? Or how do you think we could actually manage this?
If I may start, Helena, and then I would say first step would be to reduce the different amounts of plastics that we produce. So now we all have all kinds of different mixtures, which makes it almost impossible to have good recycling of plastic. So I think that would be, for me, step one. To do this, and then obviously if you have less different types of plastics, which are also much better recognizable by the public, you can also better ask them to separate and also explain why they need to do it because of the recycling process. And then I think, in the end, maybe you need to have different bins still for different types of plastics, but step one would be reducing the amount and also make it more clear what type of plastics we have.
Thank you. Helena, would you like to add something?
Yeah, I can add. I agree, Jappe. We have this problem with the different mixtures of the plastics already because we have a quite different range of polymers. But just one note: being biodegradable does not make it unrecyclable. A plastic can be biodegradable and also recyclable. For example, in Waste Biocomp, that's what we aim. Because PHAs, for example, we are developing the PHAs. PHAs are biopolyesters, and the chemical recycling process that are being applied to these PHAs is the same one that the company, it's GR3N, the one from Switzerland. It's the same process that also applied to biopolyesters or to polyesters, not exactly the bio ones, but to polyesters. It's the same process. The issue that we can have here, it's the monomers and the molecules that they obtain at the end of the process. Instead of having just two monomers that make the polymer, they can have a wide range, a mix of different monomers, which will imply purification processes before applying these monomers to repolymerization. But that's possible to recycle that. It's not feasible to have a different side stream for the biodegradable ones. If they are also recyclable, then they can go to the waste stream that we have for plastics.
Yeah, that's nice that you mentioned that, because there's also a follow-up question from Martin here about exactly this point. Like for these materials, how do you imagine these materials ending up in the waste management system? do you think that we have parallel systems, or should they actually fit in the current systems, such as the existing chemical recycling routes or the existing compostable routes? And how do consumers need to know where they would actually need to put these products?
Yeah. Ideally, they should go to the current waste streams that we have. We already have quite a depends on the countries, of course, but we can have a wide range of waste streams, the ones that go to compost, to plastics, to paper, to metals, to a wide range. So it can be quite confusing and too much troublesome to the consumers to have many more waste streams, so they are not going to use them. So these materials should be already developed, thinking the waste streams that we have.
I completely agree, and I think they already can be in those processing schemes. Only the difficulty is with the ISO norms in the end of the end product. They are not made for those biodegradable plastics. So sometimes it doesn't fit the production or the handling process by waste management companies. So maybe something needs to change on the legislation side, that it makes it easier for those biodegradable plastics to also be included in a compostable process, for instance. And on the other hand, I also think at the beginning of the circle, we need to think more about product design, because I think it starts there, and that there is the most winning part can be done there and not at the end. If we think better on how we make a product, that would make it a lot easier.
Yeah, exactly. I think last question for today from Johan. Question for Helena about the spray coating process. Could you elaborate a little bit on the actual process that you use, like what sort of liquids or carriers do you use? Yeah, if you could share anything about that.
Yeah, it's quite a simple process. It's a simple spray system. We have different kind of nozzles that we are applying, the pneumatic, the ultrasound. We are testing different ones, and the solutions that we have, they are not solutions, they are dispersions. They are aqueous dispersions of the PHAs. So we just have the PHAs in water, and we adjust the pH, of course, and